Welcome to an exciting journey into the world of antimatter, a mysterious yet fascinating cornerstone of modern physics. In this video, we'll explore what antimatter is, its role in the universe, its practical applications, and the challenges of working with it. Designed to be clear, engaging, and comprehensive, this script will guide you through the science, dispel myths, and highlight why antimatter captivates scientists and dreamers alike. Let's dive in. Antimatter consists of particles that mirror the subatomic particles of ordinary matter, sharing the same mass but with opposite properties such as electric charge. For instance, the electron's counterpart is the positively charged positron, and the proton's is the negatively charged antiproton. First theorized in 1928 by physicist Paul Dirac, antimatter emerged from his groundbreaking equation combining quantum mechanics and special relativity. This equation predicted the existence of antiparticles, mirror opposites of every particle. When a particle meets its antiparticle, they annihilate, converting their combined mass into pure energy, often as gamma rays, following Einstein's famous formula, E=mc2. This annihilation makes antimatter both intriguing and challenging to study. In the early universe, the Big Bang likely produced equal amounts of matter and antimatter. Yet today, matter dominates, a cosmic mystery known as baryon asymmetry. Scientists are still unraveling why this imbalance exists, making antimatter a key to understanding the universe's origins. Let's break down the science behind antimatter in a clear and concise way. The Dirac equation. In 1928, Paul Dirac revolutionized physics with an equation describing electron behavior at near-light speeds. Unexpectedly, it revealed that for every particle, an antiparticle with opposite charge must exist. This theoretical prediction laid the foundation for antimatter's discovery, with the positron confirmed in 1932. Quantum field theory. Imagine the universe as a vast ocean of invisible fields. Particles, like electrons, are ripples in these fields, and antiparticles are their counterparts with opposite properties. Quantum field theory uses mathematical tools to describe how particles and antiparticles emerge and vanish, making antimatter a natural part of the quantum world. CPT symmetry and CP violation physics relies on symmetries, rules that hold even when aspects of the universe are flipped. CPT symmetry, charge, parity, time, ensures that the laws of physics remain consistent under these transformations. However, CP symmetry, charge and parity, can be violated in rare cases, particularly in the weak nuclear force. This small violation may explain why matter outnumbers antimatter, a puzzle central to cosmology. Baryogenesis and leptogenesis. Why is our universe filled with matter? The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other. Yet a slight excess of matter survived, possibly due to processes like baryogenesis, involving protons and neutrons, or leptogenesis, involving electrons and similar particles. These processes required specific conditions, outlined by physicist Andrei Sakharov, and remain a hot topic in research. Antimatter is rare in nature, so scientists create, store, and detect it with cutting-edge technology. Production particle accelerators. Facilities like CERN use high-energy collisions to produce particle-antiparticle pairs, such as positrons or antiprotons. These collisions require immense energy and precision. Radioactive decay. Some radioactive materials naturally emit positrons, providing small amounts for applications like medical imaging. Cosmic rays. High-energy particles in space occasionally produce antimatter, though this is rare and uncontrollable. Storing antimatter is a major challenge since contact with matter causes annihilation. Charged antimatter. Positrons and antiprotons are held in electromagnetic traps, like penning traps, using magnetic and electric fields in ultra-high vacuums at near absolute zero temperatures. Neutral antimatter. Antihydrogen, a neutral atom, requires specialized magnetic traps to suspend it without contact, a delicate and complex process. Detection annihilation signals. When antimatter meets matter, it produces gamma rays or particles like pions, detected by sensitive instruments. Curved tracks. In magnetic fields, antimatter particles curve oppositely to their matter counterparts, allowing identification through tracking detectors. Antimatter is already making a difference in science and medicine, with potential for future innovations. Medicine PET scans, positron emission. Tomography uses positrons to create detailed 3D images of the body, aiding in early cancer detection and brain studies. Cancer therapy. Experimental antiproton beams could precisely target tumors, minimizing damage to healthy tissue. Scientific research testing fundamental physics. CERN's experiments with anti-hydrogen test whether antimatter obeys the same laws as matter, such as gravity and CPT symmetry. Cosmic mysteries. Studying antimatter helps explain why the universe favors matter, shedding light on its origins. Future possibilities. Energy. Annihilation releases immense energy, but production and storage challenges make antimatter an impractical energy source for now. Space travel. Antimatter-powered propulsion could enable faster space exploration, though this remains speculative due to technological barriers. Antimatter often sparks imagination, but let's separate fact from fiction. Myth. Antimatter is abundant and easy to collect. Truth. It's extremely rare, requiring costly particle accelerators to produce tiny amounts. Myth. Antimatter is the ultimate fuel. Truth. Production is energy-intensive, and storage is impractical, making it unfeasible for widespread use. Myth. Antimatter could be a superweapon. Truth. Creating enough for a weapon is currently impossible, and storage risks make it impractical. Myth. Antimatter defies physics. Truth. It fits within the Standard Model, though its role in baryon asymmetry hints at undiscovered physics. Working with antimatter is no easy feat. Production costs. Creating even a nanogram requires vast energy, far exceeding the energy gained from annihilation. Storage risks. Trap failures could cause annihilation, though current small-scale experiments pose minimal danger. Gravity and CPT tests. Ongoing experiments verify whether antimatter behaves like matter under gravity and adheres to CPT symmetry, critical for refining our understanding of physics. Future safeguards. If production scales up, strict regulations would be needed to prevent misuse, similar to nuclear technology. Could antimatter exist in large quantities elsewhere in the universe? Observations, like the absence of gamma-ray bursts from matter-antimatter collisions, suggest our cosmic neighborhood is matter-dominated. While speculative antimatter galaxies are possible, evidence points to matter's dominance across the observable universe. Antimatter is a window into the universe's deepest mysteries, from its origins to the laws governing reality. It powers life-saving medical tools and fuels cutting-edge research, yet its production and storage challenges keep sci-fi dreams at bay, for now. As science advances, antimatter may unlock new frontiers, from space exploration to unraveling cosmic puzzles. Thank you for joining us on this journey through the world of antimatter. If you enjoyed this video, please like, subscribe, and share for more deep dives into the wonders of science. Let us know your thoughts in the comments, and we'll see you in the next video.